Everybody, my name is Marianna Belotti. I'm a PhD student at CNAM, and I work also for Caisse des Dépots in France. And I will present you the work that it's a work in progress that we have with Stefano Secchi-CNAM, Stefano Moretti Paris Dauphine, and Maria Potop-Butucaru, Sorbonne University. We concentrate on the topic of swap. You have already assisted to the presentation of Maurice early this morning, atomic cross-chain swap. We started by concentrating on the swap problem in general, and then we considered the swap protocol in general, and then a swap protocol in blockchains, and we analyze swap protocol with both with the extensive form games and cooperative game theory. So what is a swap for us? Is a tuple composed by a set of assets, a set of owners or agents with the cardinality of the set of assets that is greater than the set of owners, because we want owners to have multiple assets, but we don't want owners to share the asset property. And we have a map B that is an ownership map, so is indicating the owner of each asset. And for the swap, what we have an initial configuration and desired configuration. So for B0, that is our initial configuration, and B star, that is our desired one, we have that this map is surjective. Then all the maps that are describing the ownership map in between the swap may be not surjective. And of course, we have also a utility function that is describing the utility of the agents, etc. So this utility function is satisfying the classic monotonic property. So for a greater asset set, we have a greater value, greater utility. And of course, as I presented before, when we start a swap, we have a desired configuration. We may end up with a configuration that is not the desired one, as in the picture. And as I said, we can have swap of assets, multiple assets, since, for example, in cryptocurrency are fungible. So we can imagine agents that swap multiple assets, but of course this is a complex situation to analyze. So we started with a single asset swap. So we imagine a scenario with agents owning just one asset and swapping just one asset. And of course, for us, a protocol, a swap protocol, is just a sequence of transfer of an asset to an owner that comes with of course a time sequence and the start and of course this asset this transfer has to be triggered in order to be has to be activated. And we can see that this our formalization can also, from our formalization, we can also derive a graph model. So we can model we can present we can present our swap with a D graph. And this is our formalization associating to each an asset to each owner. This is the B0, the original configuration, B star, the desired one. And of course, we can see that we can jump from this configuration to the D graph. What is missing in our formalization is the information on who is deciding to trigger a transfer. And then we'll see later on. But first, let's see this trivial proposition. I don't enter too much in the details, but the idea is that if we do not, if a transfer is not activated, is not triggered, we end up the owner of this transfer that is not triggered is ending up with an asset set that is lower than the asset set in the original configuration. And of course, for the utility, for the monotonicity of the utility function is less happy. And same for opposite for for the owner of the original asset that should have been swapped, that of course find himself with with a larger set of assets, and of course is happier. Then let's come to the decision function that is saying who is going to activate a transfer. And of course, this is quite important information in a swap protocol. We defined a decision function to be effective if the agent that is deciding to transfer to activate this transfer is the receiver of the asset. That means there is a transfer of an asset A to an owner O, and O is deciding whether to accept this asset or not to accept. And we can see that this decision function is really nice, because it's actually incentivizing everyone to activate. So we can end up with a national equilibrium, etc. So don't be afraid. This is just the formalization for a game-extensive form with a tree representation. So we can imagine that at each stage there is the agents that can decide whether to accept the asset or not to accept it, and this is the representation. And at each stage we have the person that has to decide. So if F is effective, so decision function effective, we have the receiver that decide whether to accept or not. And of course, it's quite trivial, but the proof is not so complicated, that if F is effective, we end up with an equilibrium, a perfect equilibrium in subgames, in the sense that we can imagine to decompose the game in small subgames, so in small subtrees, and in this case, the action follow the protocol, meaning activate the transfer, is always the best response strategy. So it's always the one that is maximizing the utility of the agent. Okay, but and the stronger result is that also it's not only the if part that is true, but it's also the only if part is true. So if we have a decision function F, a decision function F is effective if and only if there is a subgame Nash perfect equilibrium that says activate at each stage, activate the transfer. And the proof, I will give an idea, is done by contradiction. So we assume that F is not effective. What does it mean? We can have two situations. Basically, we can have the situation where the one that is activating the transfer is the one that is losing the asset and transferring the asset to the other owner. And of course, for the proposition that you saw at the very beginning, we end up with a larger set of assets and a smaller set of assets, and of course is not incentivized in activating the transfer. And what is interesting is that we can imagine configuration where the activator is an agent that is external to the transfer. So, for example, A is activating this transfer here, and the proof says it's quite trivial. We can imagine a lot of protocols that can incentivize this, but we arrived at a point where there is an agent that has to make the decision, but he is not incentivized at doing it. Okay. And of course, we miss something. So there exist in reality protocols that have a decision function that are not effective. So that they have activators that are not just the receiver of the asset. But what is missing? It's missing a penalty mechanism. 2 minutes, okay. So the protocols with the F not effective may work if we construct a penalty system that incentivize to follow the protocol, so that it incentivize agents always to activate the transfer and not to not activate. And of course, the penalties should be different for the two cases that I presented in the proof. Just quick overview, what we did with cooperative analysis, with cooperative game theory, is to take the hash time lock protocol and to study if to imagine a situation where agents wants to take advantage of the system. So they want to take advantage of, for example, denial of service attack, network problem, etc., problem in communication between the nodes, and see if they can end up gaining something. So they can form a coalition and deviate from the protocol. And the strategies are always the follow and deviate the protocol, so activate or not activate the transfer. And the payoff are the one that Maurice described in his paper. So we can end up with a free rider discount, so in a good situation, or we can end up with the deal. So everything is swapped, no deal. We came back to the original situation. Underwater, we lose money. And of course, we imagine a situation with the hedonic games that consider preference profile that is a preference profile that is the same for each player in the game. They don't want to lose money. Okay. And we end up with this result. Yes, the last slide. That states that we have a coalition structure, a configuration with the leader of the swap that is the one that is activating the swap at first, and all the followers together that is individually stable, in the sense that any player has an incentive to abandon his coalition and to join another one. And they prefer to stay where they are. And this is showing an asymmetry between the players of the swap. So what is interesting? What is interesting? What was interesting to see was that effectively there is an asymmetry between the swap initiator and all the other intermediaries. And this asymmetry, this is an attempt to prove this asymmetry and to actually to say the goal is to arrive to give a price to this asymmetry, in the sense that, okay, you don't want to be the initiator, you have to pay something, and that's the goal of this work.